Hello everyone, my name is Rashid Kibriya. I am a PhD student at University of Florida. I am quite happy to present our work at International Test Conference 2022. Today I will talk about the FSM extraction engine that we have developed at the RTL abstraction. Here is shown the outline of my presentation. First, I will talk about the motivation behind our work. Then I will discuss about the contributions we made in this paper. Next, I will talk about the basic principle of control FSM extraction. Then I will go over the overview of the RTL-FSMx framework. I will present the algorithmic flow of RTL-FSMx. Then I will present some of the experimental results on some open source benchmarks. I will also show a case study on memory controller IP. Next, applications of RTL-FSMx will be discussed. And finally, I will conclude my presentation. First, I want to talk about the motivation behind the development of RTL-FSMx. Existing FSM extraction techniques from RTL design have longer runtime, and these techniques also suffer from inaccuracy issues to extract all control FSMs. Sometimes they also require manual decision to detect the control FSMs. Existing state-of-the-art commercial synthesis tools are good examples of this, because if it cannot detect FSM, control FSMs automatically, then user need to specify it. So this approach is semi-automated and requires a priori knowledge of the control FSMs present in a certain design. Moreover, these approaches also have inherent reliability issues in the FSM extraction process, because these techniques cannot extract control FSMs from extremely complex RTL designs sometimes. They also suffer from scalability issues in analyzing large SoC level RTL designs. For example, program source code slicing method, which actually extracts a part of the program, analyzing line by line. So it has obviously inherent scalability issues in analyzing very large sized design. Now I will discuss about the contribution we made in this paper. We have developed RTL-FSMx framework for automatic extraction of all control FSMs present in the RTL code. Extraction of all human readable state transition graphs separately for each of the detected control FSMs were also our target. Moreover, faster and more precise recognition of control FSMs were achieved. RTL-FSMx stands for Register Transfer Level Finite State Machine Extractor. So this framework is technology independent. It is actually a pre-synthesis solution, a pre-synthesis FSM extraction technique, and a pure software-based solution based on static analysis of the provided RTL code. The framework is very fast, accurate, and reliable, and also our framework is scalable to large and highly complex RTL designs. Here is shown the FSM minimum extraction region, or the generic architecture of the control FSM. The generic architecture of a control FSM has basically two parts. The first one is the state transition logic, or STL, and the second one is the state register. State register is the sequential part of the control FSM. This state transition logic and state register, they form the FSM minimum extraction region. This region is very important to extract the state transition graph perfectly. And the output of the state register also drives some output logic, which actually provides us the control output signals from this FSM. The basic principle for any FSM extraction technique is quite simple. First, we need to identify the state register. Then we have to detect the state transition logic. And finally, we need to extract the control FSM state transition graph. Here is presented high-level overview of the RTL-FSMx framework. So the input RTL designs are written in Verilog and they are taken as input by PyVerilog's abstract syntax tree generator. PyVerilog is an open source Verilog HDL compiler which actually provides us the abstract syntax tree representation of the input RTL design. This abstract syntax tree is taken as input to the major module, that is the FSM recognizer and stage extractor, which actually provides us an exhaustive FSM extraction report from the RTL. And this FSM extraction report consists of state variable, state vector, state encoding, state transition graph in both text and graphical format, the FSM input signals, and finally the control output signals that are generated from the control FSM. Now I will discuss about the algorithmic flow of RTL-FSMx. That means how it actually works. There are several steps, so total 8 steps. The first step is to generate the AST representation or the abstract syntax tree representation of the provided RTL design. The abstract syntax tree or AST acts as an intermediate representation of the RTL code, and it is somewhat language construct independent. There are some advantages behind using AST for analysis. First of all, the AST representation actually makes the entire RTL design code in a tree-like structure. So it makes the analysis process of the provided RTL code much easier. And also, it enables node-based analysis on the AST, which ultimately bypasses unnecessary line-by-line analysis of the input RTL code. Here is presented an example of it. So in the left-hand side, you see an RTL code representing a register, and on the right-hand side, we see its abstract syntax tree representation generated from PyVerilog. Here is presented the algorithmic flow of the FSM recognizer and stage extractor module, which is the core part of RTL-FSMx. There are a couple of steps. The FSM recognition process starts with detecting all the sequential blocks of the RTL code. Then we identify all the case statement controlling variables. Next, we go to recognize all the clock and reset signals present in the RTL design. Finally, we identify all the state variables of the control FSMs, determine the state vector, reset state, and next state variable. And also, at the last two steps, we detect all the states of the control FSM and construct the state transition graph and identify the FSM input signals in the process, and also we report the output signals generated from the FSM. In the second step, we actually detect the sequential blocks of the provided RTL code. It is because identification of always blocks with sensitivity to S-trigger signals, they actually represent register block in an RTL code. It comes from the guideline or template for describing a certain register in HDL code. Always blocks which does not have any S-trigger signal, they basically correspond to combinational logic blocks or latch units. So they are discarded by RTL-FSMx. The sequential part of a control FSM is also known as the state register of the control FSM. Here I have shown two illustrative examples of it. So in the left-hand side, we see the single register with asynchronous reset, and here we see both the clock and reset signals are present in the sensitivity list. But on the right-hand side, we see we have multiple FSM state registers, and they are declared in the same block, and they are driven by synchronous reset because only clock signal is present in the sensitivity list, and we find the reset signal in the if block. Here is presented an example of a combinational logic block. So here we see the sensitivity, it depends on all the inputs. No input here is edge triggered and all the inputs are basically level triggered. So this block actually corresponds to a particular combinational logic block, and it is taken from an open source RTL design. The third step is to identify all the case statement controlling variables. It is a crucial step because some of the variables which are case statement controlling variables, they are potential state variables. One thing needs to be mentioned here, that not all case statement controlling variables are state variables, but all the state variables are case statement controlling variable. In the fourth stage, we recognize all the clock and reset signals present in the RTL design, and we do this via analysis of the sensitivity list, and from there we get the clock signal and reset signal if that is present. Analysis of the if statement is actually required to recognize the reset signal correctly. Then we determine the clock signals, and one thing needs to be mentioned here, that RTL-FSMx does not terminate immediately upon encountering the first clock signal. It actually analyzes all the always blocks with edge trigger signals and finds the register and gets the clock signals, all the clock signals from there, and all the other combinational logic blocks are discarded. This makes RTL-FSMx unique because with this feature, multiple domain clock signals can be detected. And here I have shown an example of how a reset signal is specified in the if statement of a certain RTL code of a register. In the fifth stage, we identify all the state variables of the control FSM. A state variable of a particular control FSM is a case statement controlling variable which causes a state transition of the FSM. More precisely, these variables are all the case controlling variables having two properties. The first property is that these case statement controlling variables should be present in a certain sequential block of the RTL, which represents a certain register. And also, these state variables should be assigned to next state variable, or state encodings should be assigned to it. And here we actually see there are multiple control FSM state variables. It can be specified in a certain design using this format. And we see this state variable is controlling a case statement. And on the right hand side, we see two FSM state variables are declared, and they are described in two different always blocks. So both of these scenarios are handled by RTL-FSMx, which makes RTL-FSMx to be capable of extracting all the clock signals and reset signals perfectly, and also the state variables from the RTL description. Here is presented more illustrative examples. We see here non-control FSM register variable, say round CTR range. It is not driving any case statement controlling variable. So even though it has a very good template similarity with the FSM, but it is not, it will be discarded because this non-control FSM register state variable does not drive any case statement controlling variable. The control FSM register state variable always drives some sort of case statement block, and from there we can actually make distinction between a control FSM state variable or non-control FSM state variable. And we also see here the one state is actually assigned to the FSM state variable, and here we see some assignment to a non-control FSM state variable. It actually represents a counter. So these sort of counters are discarded perfectly by RTL-FSMx. in step 6, we actually find the state vector representation, identify the reset state and next state variable. In this stage, we report all the state vector, reset state, and next state variables present in the RTL design. Once the control FSM state variable is detected successfully, then we can identify the size of the state register, and hence the state vector can be easily determined. The reset state is identified by analyzing the if statement block that I have already mentioned, and in this stage, the next state variable is also detected in case of two process model. And in the left hand side, you see an FSM written in two process model. Here we see we have two reset states, and the reset states are declared always in this format. Upon some reset condition, we actually go to the reset state, otherwise we transit to the next state. So it has obviously definitely a certain template in two process model. Similar thing also applies for FSM written in one process model, and here we see the reset state declaration and also the other assignment to the control FSM state variable for extracting the state transition graph. In the seventh stage, we identify all the FSM states and construct the state transition graph, or in short STG. In this stage, detection of the node containing case statement driven by state variable are done, and we actually recognize all the states of the FSM with their associated encodings. State encodings are normally declared using parameter or local param type variables. It is true for state encoding style using the symbolic format. Sometimes states are encoded using numbers with appropriate number basis. For example, binary, decimal, octal, hexadecimal, or sometimes using mixed encoding styles. This step is done via getting all immediate descendant nodes of the selected case statement, the node of the ST, except the default case if that is present. So after this stage, we automatically identify the FSM encoding practice, and RTL-FSMx reports which FSM practice has been utilized, for example, either binary, gray, or one hot. We also represent the encoding of the states using binary format, and analysis of the state or next state variable assignments are done to construct the STG. Here are shown some illustrative examples. We see the state variable assignment to this state variable, and here these fields are actually the destination states, and the source state is coming from the case statement condition type thing. So I have also marked here the where you can find the destination state. From their state transition condition, the FSM input signals can be also derived. And here we see the control FSM state register. The next state variable is assigned to the states of the FSM. And here is some more complicated thing that RTL-FSMx can also handle, because this FSM is really very complex. It comes from one control FSM of the Open MSP 430 core. And you see here we have so many destination states, and the template is a bit different, but RTL-FSMx is able to handle that. In step 8, all the FSM input signals, control output signals are reported, and it is actually obtained via analysis of the state transition logic RTL description. FSM input signals are extracted from the active state transition conditions, and it is mainly done by analysis of the statements of all the assignment statements to the state or next state variable. The active FSM state transition conditions are also extracted and stored. The control output signals generated from the FSM are the signals which are influenced by the state variable. The output or intermediate signals influenced by the control FSM state variable. One example is shown here. We see the control output signal, and we also see an assignment to this control output signal. In this way, all the FSM inputs, outputs, and other important parameters, that is the exhaustive FSM extraction report, is generated by RTL-FSMx. Here is shown some of the experimental results that we presented in our paper. If you look at the runtime of RTL-FSMx, you will find that it is so fast. It can analyze all the RTL designs within just a few seconds, even for an SoC level design. And all the RTL designs here obtained from open source repositories. And you will from this you will be able to see that RTL-FSMx is 100% accurate, because it is capable of extracting all the control FSMs from the RTL design perfectly. The time complexity of RTL-FSMx is order of m, where m represents the total number of always blocks present in the RTL code. The space complexity of RTL-FSMx is order of n, where n is the total node count of the AST. And this runtime, which is mentioned here, is actually for the entire RTL-FSMx framework. That means starting from step 1 to step 8. Here I have presented a case study on an open source core, that is the memory controller IP. It is an extremely complex memory controller core. It has a control FSM state register of size 66 bits. That means it is basically an FSM with 66 states. The FSM was encoded using one-hot encoding scheme, so it is really very complex. Intel's Quartus Prime detected the control FSM, but it actually failed to extract the state transition graph. And here I have shown the graphical control FSM STG, which was extracted by RTL-FSMx. Here I have shown what actually happens if you try to analyze the memory controller IP with Quartus Prime. You will find that the FSM was detected, and Intel's Quartus Prime actually shows you the detected FSM with this yellow box. But when you click on that, you will find it will open up a blank page. It represents that no strategy was extracted by Intel's Quartus Prime. But our developed RTL-FSMx actually extracted that successfully. It is basically due to the complexity of the state transition logic and the state transition graph. Finally, I will talk about some of the applications of RTL-FSMx. RTL-FSMx can be used to localize and extract the control FSM description in the RTL code. Fault injection aspect in the RTL abstraction is doable because it extracts states and transitions of the control FSM in the RTL description perfectly. Assessments can be also performed utilizing novel mathematical metrics. You can also use RTL-FSMx for FSM-based watermarking or logic locking, because RTL-FSMx yields the state transition conditions for each of the state transitions present. Moreover, RTL-FSMx can also aid you to perform FSM reverse engineering at the RTL abstraction, because it generates an exhaustive FSM extraction report of the input RTL design. It is quite handy for analyzing third-party IP codes to get a quick idea of the control flow of the design. Apart from these security applications, RTL-FSMx can be also used for a notable non-security application, that is for the pre-synthesis verification of the control flow of the entire RTL design, because of the accuracy and reliability of RTL-FSMx. To conclude, RTL-FSMx enables control FSM extraction from the input RTL design within just a few seconds, even for an SoC level circuit. and with 100% accuracy. It detects and localizes all the control FSM description present in the RTL code, which makes it useful for numerous security and verification applications. Our future research incorporates utilizing RTL-FSMx for performing fault injection assessment, watermarking, and logic obfuscation at the RTL abstraction. Moreover, RTL-FSMx can be enhanced or extended to support other languages, for example, VHDL or System Verilog. The concepts of RTL-FSMx you can also use to extract control FSM from system C level designs as well. Finally, we have been able to develop a completely standalone RTL-FSMx tool, and the demonstration is already available online. If you are interested to watch this demo, please do it. And if you think that you may require RTL-FSMx for your research, you may directly contact us. That was all from me today. Thank you. If you have any questions, please feel free to ask.